Okay. Hi, I'm Seth. I'm a fifth-year grad student at Penn, and this is joint work with Aaron Roth and Stephen Wu. And thank you to everyone, particularly the West Coast people, for showing up at what is the crack of dawn for them. Okay. So in this paper, we build a theory for how to employ non-private heuristics. So by that, we really mean optimization oracles to solve computationally challenging problems in differential privacy. And there are two types of problems that we focus on. The first kind are hard absent privacy. So these are learning problems. So agnostic learning of basic classes like hyperplanes, conjunctions, is hard even absent privacy. And the question there is then, given a heuristic for solving the non-private problem, can we use it in a black box way to solve the private problem? And so the sort of thrust of this direction is to derive practical algorithms about which we can still prove formal guarantees in differential privacy. And the second type of problem are problems that don't even make sense without the constraint of privacy. So generating private synthetic data. And this means, given a data set D, to construct a data set D prime in a differentially private way such that D and D prime match on a class of concepts that we care about releasing. Then instead of releasing D, we can release D prime, and the end user can compute whatever they want on D prime. Okay, but due to time constraints, we're going to focus on the first problem, especially since we leverage it to solve the second problem in the paper. Okay. So here are the results. Our first result is a natural reduction from efficient non-private learning to efficient private learning for any concept class that has what's called a small separator set, which is, maybe it's a somewhat arcane property, but many of the concepts that you would encounter do have a small separator set, for example, discrete hyperplanes, decision lists. And so this is a nice example of an algorithm that its privacy guarantee depends on the use of a non-private heuristic. And we can prove that it's differentially private, but conditional on this non-private heuristic succeeding perfectly. And that motivates the main technical result of the paper, which says, suppose that we want these privacy guarantees to hold no matter what, and we're fine with the accuracy guarantees being heuristic. Can we give a reduction that takes in an algorithm whose privacy guarantee depends on a heuristic and make it robust to failure of that heuristic? So failure of, say, the optimization oracle. And we're able to do that in the case where the oracle is certifiable, meaning we know when it fails. And then as an application, this gives the first oracle-efficient algorithm for generating private synthetic data for contingency tables, which is kind of the main application. Okay, so let's quickly define differential privacy. This is probably not the best way to learn the definition if you don't know it already, but differential privacy means that given two neighboring data sets, D and D prime, which differ on one data record, and some set omega, it says equals x there, but any set omega, the probability of landing in that set when you run the randomized algorithm on D versus running it on D prime doesn't differ by more than a multiplicative factor of e to the epsilon and an additive factor of delta. Okay. So here's the sort of useful properties of differential privacy, which are used in every paper. It's closed under post-processing. So given a private algorithm, if you apply some possibly randomized function to the output, it doesn't change the privacy guarantees, which is intuitive because it's not touching the private data at all. And differentially private algorithms compose well. So if you have a sequence of possibly adaptively selected differentially private algorithms, you can just add up the privacy guarantees, or you can really get root K composition with a slightly worse expression for the parameters. So you can compose these differentially private algorithms. And the upshot there is that you can go about designing private algorithms in a modular way, which is one reason why it's such a popular area. And all you have to do is sort of keep track of the different parts of your algorithm and keep track of your privacy budget in each of these different parts and apply composition. Okay, so the good news then is that under differential privacy, we can achieve powerful statistical disclosure. So we can do pack and agnostic learning. We can generate private synthetic data. As we saw in Stephen's talk yesterday, we can answer exponentially many adaptively chosen queries. But the downside is that all of these problems are hard, are computationally hard under privacy. And so where do we go from this? So let's take a step back and sort of draw an analogy to the situation in machine learning, where again, the basic learning problems are computationally hard, agnostic learning problems, even for things like conjunctions and half spaces, but this hasn't stopped the progress of machine learning. We still solve harder problems than this every day, and the reason we can do this is because performance is empirically verifiable. We can solve a problem, produce a model, and check the accuracy. This is not the case in differential privacy. In differential privacy, we need a proof to show that the algorithm is actually private. And so while worst case hardness is irrelevant in machine learning, up until this point in differential privacy, we haven't been able to use these heuristics. And so the goal of this paper is to use heuristics that may fail for differential privacy problems without giving up provable guarantees. Okay. So here are the basic definitions. X is the data universe. C is our concept class. A weighted data set is just X's with weights Wi in -1, 1. And now we'll define what we mean, what we mean by the learning and optimization problem, and therefore what we mean by an oracle. So the learning problem is just to find the F star in the concept class that has the maximal accuracy, or alternatively, we could think about minimizing the risk. And the synthetic data generation problem is kind of as I described before. Given D, we want to release D prime such that for all F and C, F of D is close to F of D prime. So that's what we mean by releasing synthetic data for a concept class C. Okay, and this then corresponds to 3 types of oracles. The first is a perfect oracle for this weighted optimization problem. This is an oracle that we assume always solves this problem exactly and returns the maximizer in the concept class C on the weighted data set. The second kind is a heuristic oracle. So this could output any concept in the class. No guarantees, all bets are off. And the third, which is the regime where we can actually prove something, is a certifiable heuristic oracle. So either it succeeds and solves the optimization problem and outputs a certificate of correctness, or it fails and just outputs fail. So we can think of integer linear program solvers like branch and bound as a motivating example for a certifiable heuristic oracle. Okay, and this corresponds to 2 notions of differential privacy in this talk. The first we'll say is non-robust differential privacy. So this is an algorithm who is differentially private, conditional on access to a perfect oracle. And the second kind is robust differential privacy, or i.e. real differential privacy. So no matter what, even if the oracle fails, the algorithm is always differentially private. And so the reduction will be going from 1 to 2. Okay, now we'll actually get into some results. So we'll show the first result, which is the natural reduction from non-private learning of concept classes that have this universal identification set property to private learning of those same classes. Okay, so a universal identification set for a concept class is exactly what it sounds like. It's just M examples such that those M examples uniquely identify every element in the class. So any 2 concepts in the class differ in labeling at least 1 element in that set. And many natural classes have universal identification sets. For example, for conjunctions or disjunctions, it would be the standard basis. Okay. So now we get to our first result, which is an oracle-efficient, non-robustly private learner for any of these classes, which we call the RSPM algorithm in the paper. And it's a very natural algorithm, even among Oracle efficient algorithms. So all you do is you just take the original data set, you have a separator set for that concept class, you augment the data set with the elements of the separator set. So you basically throw in D, if that's the size of the separator set, more examples to your data set. You randomly weight those points with Laplace noise, kind of scaled to the size of the separator set over epsilon. And then you just throw it into the optimization oracle. So given any black box for solving the non-private problem, you just augment your data set with a few examples, and you can use that oracle for solving the problem. Okay, so now I'm going to prove that this is private using a technique I like to call the wiggle method. And essentially the wiggle method is fix some D and fix a neighboring data set D prime, and then fix some realization of the noise. So the noise here is the weight for the elements in the separator set. And if you can show that by just wiggling that noise a little bit, so there's a nearby value setting of the noise, such that on that neighboring data set D prime, you would output the same maximizer as on D with the unwiggled noise, then the probabilities of outputting those F star on D and D prime must be similar. So essentially it's like if for any realization of the noise that would cause you to output F star on D, there exists a very similar realization of the noise that would cause you to output it on D prime, the marginal probability of outputting F star on D and D prime should be close. Okay, so how do we wiggle the noise? So suppose that we've drawn these WI weights for the elements in the separator set from this Laplace noise, and on D, we output some F star. What we do is we look at how F star labels all of the elements of the separator set. And we essentially increase the score of F star on all of those examples by increasing the noise by the corresponding direction on F star. So if F star labels it correctly, we add 1 to the noise in that for that separator set element. And if F star labels it incorrectly, we would subtract 1. So we wiggle the noise advantageously to F star so that the score of F star is going up by D, which is the size of the separator set here. Then even if we're on D prime, F star has to be output if the noise was really the wiggle noise, because for any other candidate F that could be output on this neighboring data set, because it's a separator set, F and that element and F star differ in classifying at least one of those elements, and F star has already increased its score on that element. And it was the original maximizer. And so since we've only changed one data point, and F star's score has also gone up from wiggling the noise relative to any other concept in the class, F star still has to be the minimizer. So that's the intuition without going through the math. Okay, and so we're able to prove that this induces error order size of the separator set squared over epsilon n. And if we use Gaussian noise instead of Laplace noise and relax to approximate differential privacy, that becomes size of the separator set raised to the 1.5 over epsilon n, which is still suboptimal by a factor of square root of the size of the separator set, so root d. So that's an open problem, whether we can remove that factor of root d. But crucially here, the privacy depends on the correctness of the oracle. So that motivates the main result of the paper, which says, suppose we have an algorithm like the one we've just seen, where the privacy guarantee is conditional on the success of the oracle. Can we give a reduction that guarantees that it's robustly differentially private, no matter what the failure of the oracle? Okay, and so before I launch into just the rough overview of this result, why is this not obvious? So one thing you could think to do is, and we did when we were thinking about this at first, we were like, okay, suppose we know that the heuristic oracle fails with some small probability. let's just run it until we guarantee that with at least probability 1 minus delta, we get some successful run of that oracle, and then output that. Then we know it's delta close in total variation distance to running the algorithm with a perfect oracle, so which was epsilon 0 dp, and so the whole thing should be epsilon delta. Like, okay. The problem with that is that we don't know what the failure probability is of the algorithm, and okay, so then you think, all right, let's just estimate that privately and account for the error in the estimation of that. The problem with that is it's an arbitrarily high sensitivity quantity. The oracle could say, if Seth's in the data set, I fail. I'm not doing this. So changing one person in the data set could change the failure probability an arbitrarily high amount, and so you can't estimate it privately either. And that motivates sort of the overall structure of this algorithm, which is a so-called subsample and aggregate scheme, which is what we use in differential privacy to sort of force low sensitivity. So what we do is we take the data set, we partition it into order 1 over epsilon different pieces, each of which draw elements from the data set without replacement. Then on each of those pieces, we do kind of that scheme. We run the algorithm order 1 over delta times. And if it ever fails on that piece, we label that piece as a failure. And if it succeeds every single time, we label it as a success. Then we tally up the number of successes, and we say, with appropriate noise to preserve privacy, if at least 1 over epsilon of those chunks have succeeded, then we can uniformly at random choose one of the successes and release it. Otherwise, we say that we failed. Okay. So, good, 3 minutes. So before we delve into the exact proof, a few comments. So the first is negative. It's that the running time of this is 1 over delta. So since delta can be polynomially small in n, it's still polynomial time, but we can't take delta exponentially small in n. Okay, and the error overhead is essentially a square root factor worse than before we do the reduction. This is because when we split into the different chunks and run the algorithm, A, we're only running it on an epsilon fraction of the data set, and B, we actually have to decrease the privacy parameter, which you'll see in the proof. So instead of getting d root d over epsilon n, we're getting d root d over square root epsilon n. Okay, so here's the privacy analysis. There's 2 types of outputs. There's a failure and a success, where the success corresponds to just outputting an element. The failure is obviously private. The only time at which it can fail is in the step where you tally up the number of successes on the chunks, and that is just a simple application of the Laplace mechanism. Every data point is in at most 1 chunk, so it can affect at most 1 failure. So it's sensitivity 1. We add Laplace 1 over epsilon noise to the count. We're good there. So the tricky thing is actually when you succeed. Okay, so now here are two facts about when you succeed. So when we succeed, with high probability, at least 1 over epsilon partition elements have survived. And all of these have been run order 1 over delta times. And so with high probability, they're all epsilon delta private on that chunk, because they're delta close in total variation distance to running with a perfect oracle. So here's the tricky part, and which chunks survive is not differentially private. So suppose we fix some data set D, and we're on some data set D prime, and we have some set omega that we're concerned about an outcome landing in. And under D, if we focus on just the first chunk, let's assume that the probability of A run on that chunk landing in omega is very high. And on all the other chunks, it's basically 0. So all of the probability mass of this outcome corresponds to 1 chunk. As we mentioned before, on a neighboring data set, the adversary could just choose to make that chunk fail. So all of the probability mass could be removed by the adversary here. And so this would cause the probabilities of being in omega on D and D prime to be very different, which is not differentially private. And the reason that can't happen is because the probabilities, basically that situation can't happen. The probabilities for all of the different chunks for any event omega are very close, i.e., over the draw of the different chunks with replacement, we can show that the probability of being in omega is well concentrated. Okay? And I'm sort of running out of time, although these are the last two slides, but the reason for that is a simple application of Azuma's inequality, but that is the reason why on those chunks we need to take epsilon much smaller. And this goes back to an observation that has been made in previous papers, that differentially private algorithms are distributionally accurate when epsilon is on the order of 1 over root n, meaning that they concentrate around, like if the data set's drawn from a distribution, they concentrate around their expectation. So we're basically able to sort of union bound over all the chunks and show that this negative case where one partition fails, D1 prime, would only remove an epsilon fraction of the probability mass, because all of those other chunks have similar probabilities of being in omega. And so that's how we show that the whole thing is differentially private. And if you want to understand that better, please read the paper, but we do think that is sort of a unique privacy analysis that we hadn't seen before. And so lastly, I'll close with open questions. So the first is the overhead necessary for private learning? Can we remove this square root of D factor in the RSPM algorithm? Can we get a better reduction? The order 1 over delta running time seems very hard to avoid because of the need to sort of prove that the total variation distance is less than delta. But maybe we can get a better dependence on epsilon and n. So maybe this distributional privacy and concentration inequality argument is overkill. And is it possible to get anything when the heuristic is not certifiable? All right, thank you. No, Matt's giving it.